Hey guys, welcome. First of all, I hope that the test on the syncing between audio and video holds up and that we have good quality here. If there's a problem, let me know. We can go back and we can recover this lesson, hopefully in a brief matter of time in class, even though that would cut away from some multiple choice review. All right, so what we're going to do with this video is we're going to review linear regression concepts, talk about scatter plots, correlation coefficient, residuals plots, R-squared just a little bit, high influence, high leverage points, all that stuff that you guys said, hey, from first semester this either didn't stick or it was tough to try to fathom during the multiple choice. So let's start with the basics. Let's start by talking about the association of a scatter plot. Okay, so I'm going to draw 4 scatter plots here so we can have a few things to reference. And for each, we'll draw an x and a y axis, or variable name, on those axes. X, y, x, y, x, y. Okay, all right, so let's look at a first scatter plot that is maybe something like this. So when you're talking about, if you're asked about the association of a scatter plot, the association boils down to strength, direction, and form. Here you see in terms of, let's go direction, form, and strength. Let's put the 3 in that order. The direction is positive because it's going up from left to right. It's got, we'll keep the current color scheme. I don't want Windows Help and Support ever, ever, ever. Form, I want, or it is linear. And then the strength here is strong because you've got a good clustering of the coordinate pairs of x and y. Recall that each one of these guys is an xy coordinate pair. Okay, I'm using the variables xy generically so we can get through the explanation faster. Remember too that x is always your explanatory variable, y is your response. If you were asked to build a scatter plot of data, you need to be smart about which data would explain the other, or which variable would explain the other. If I have number of not gallons, but glasses of milk that students drink here at Yorktown High School weekly as one data set, one variable set of data, and my second variable's worth of data is the height of those students. Obviously, I'm not going to use the height to explain the amount of milk that they drink. I might try to see the flip of that. Is getting good calcium intake weekly a good predictor of students' height? Okay. So again, there's direction, form, and strength for a first scatter plot. You might see a scatter plot look something like this, in which case this is still positive because it's quadratically positive. It's going up on the left side and on the right. It moves towards infinity as you go further left or further right. So again, quadratic form. And here, I mean, I guess it's a moderate strength. It's not as tightly clustered as the first scatter plot is. Okay? Third scatter plot of data, let's draw something that's really spread out. Okay, so here you've got a negative direction, still linear, and then the strength is weak. Okay? Well, finally, you might see a scatter plot that looks something like this, where you really don't have any direction. You've got no form, and the strength is weak. Okay, all are possible, but again, association of the scatter plot is strength, direction, and form. Okay, on to slide 2. In slide 2, we're going to start to talk about correlation coefficient. Correlation coefficient measures the extent to which your data follows a line. This is on your AP Stats reference sheet. If you're not looking at that as you're going through, let me rewrite that. If you're not looking at that as you're going through these review multiple choice questions, you're doing yourself a huge disservice. Get familiarized with the AP Stats reference sheet. At this point, I don't care if you have extra stuff written on it or not. I just want you to be familiar with the equations they're going to give you on the exam. Virtually everything that you need for linear regression or for scatter plots, all those equations are already on the reference sheet. So don't commit them to memory. Commit to memory where they are on the reference sheet if you need them. Okay. All right. So with another scatter plot here, we'll draw a little bigger. We've got x and y variables again. Let's set up some sample data. And it's not giving me all the points that I'm hitting here. Maybe I'm punching it too hard, I'm not sure. Anyway, okay, so there's a scatter plot of data. And through this scatter plot, we're going to draw x bar. That's the center. Oh, wait, that's not right. Y bar. Y bar is right there. Y bar right here, and then x bar right here. Okay. All right. So what does that represent? Where the two lines hit, that's the very center of the data set in some sense. And y bar is the average of all the y values for all these points. Okay. While as x bar is the average of all the x values for all these points, et cetera, et cetera. Okay. Hopefully that's clear. Vertical and horizontal lines representing those two. All right, so the correlation coefficient is calculated as follows. It looks at all the individual points. This is why we never calculated this by hand, because when you've got a scatter plot of lots of coordinate pairs, it becomes cumbersome really fast. But this guy, for instance, it's going to say, okay, we are going to take the sum of all the coordinate pairs, and for each coordinate pair, we'll multiply its z-score for x, the number of standard deviations it is away from the center of the x data, times its z-score for y, the number of standard deviations it is from the y data, or from the center of the y data, okay? And we're going to see if that has a positive or a negative effect upon the correlation coefficient, remembering that the correlation coefficient is always between -1 and +1. On the -1 end, the data perfectly follows a line and it's going downwards. On the +1 end, the data perfectly follows a line and it's going upwards. A correlation coefficient of 0.5 or 0.25 means that it's going upwards because the sign is positive, but it's not necessarily following a line perfect. Well, it isn't following a line perfectly. Okay, so for this, getting back to this point that I circled, this individual point has a positive influence, upon the correlation coefficient. And you've got a lot of points through here. Anything, so to speak, in your first or your third quadrant with respect to the center of your x's and the center of your y's, anything in the first and the third quadrants has a positive influence upon the correlation coefficient. While a point over here, when the correlation coefficient is looking to see what its influence is upon the data set, it sees that, okay, well, yeah, you've got a positive z-score for x, you are a positive number of standard deviations above the mean of the x, but you've got a negative z-score in y. So your net effect upon the correlation coefficient is a -1. That's why, because the correlation coefficient cuts through the center of the whole scatter plot, you're going to generally have some points that will counteract the generally positive or generally negative effect of the rest of the data. Okay? So there's a little bit about correlation coefficient. A lot is there in that picture. If you have questions, approach me with them. Ask me in class, feel free to do so. Okay? Third slide, we are going to look at, the regression line a little bit. Okay, so if I draw a scatter plot here, x and y, and let's make our data relatively tightly clustered. Okay, all right, we've got our data, and the correlation, or not the correlation coefficient, the regression line is y hat equals b naught plus b1x. And you guessed it, it is also in your AP Stats reference sheet. B naught being the parameter, the number that determines what the regression line is, that is not touching x. It's the parameter not touching x. It is the y-intercept, okay? And the y-intercept, remember, is what the regression line would predict y to be doing right here when x is 0, okay? If you plugged in 0 for x, what would the regression line predict? Well, perhaps more interesting is the slope. Slope. And that's calculated, this too on your reference sheet, if you were asked to find the slope of a regression line, there are a few ways to do it. Sometimes, as you guys have seen from your multiple choice questions, it may be present in a table of output that you need to interpret. But if you're given some numbers to work with, your slope is calculated as the correlation coefficient times the standard deviation in the y variable over the standard deviation in the x variable. Okay, again, that too is on the reference sheet. Every regression line ever will always go through the center of your x data and the center of your y data. Okay, your regression line sort of hinges upon that center. And it comes from the fact that your regression line is built off of the correlation coefficient, and the correlation coefficient cares about the center of the data. Okay? Last thing I want to say here, the regression line, hopefully we're all comfortable with this. It doesn't necessarily tell you what will happen for y. It tells you what we would expect to happen, what we would predict to happen for y. So for instance, the regression line right here would take a particular x value and not give you necessarily what happens in the real world, but it'll tell you what we expect to happen, y hat, a predicted y value. Okay? So again, thinking of x and y as a number of cups of milk drank each week and height, it would tell you, okay, given a particular number of cups of milk drank each week, what we might expect a particular student's height to be. Okay? All right, so with the regression line, you've got two things that you need to pay attention to in determining the appropriateness of a regression line through a scatter plot. First of all, you need to be looking at your residuals, and in particular, your residuals plot, which you can graph on your calculator. You first take linreg of your lists, L1, L2, okay, and it will calculate the residuals, and then you'll graph a scatter plot, your residuals plot. Is going to be a scatter plot where you set up your X list is L1 and your Y list is resid or resids. I can't remember if it's with the S or not on your calculator. Regardless, that's how you'll set up a residuals plot. Second thing you look at that's less important is your R squared value. This takes on values between 0 and 100, and it tells you the percent to which the variability that you see in Y can be explained by the regression line. 100% means that a lot of what you see happening in Y can be explained by the regression line. 0% means none of what you see happening in Y can be explained by the regression line. Okay, so let's take a look at a sample scatter, or not scatter plot, but residuals plot here. We'll take a look at 2. I'll put E on the vertical axis, X on the horizontal. E on the vertical, X on the horizontal. Lowercase e is your variable to represent an outlier, or not an outlier, a residual. And I'll put what the calculator would give you through any residuals plot on my scatter plot as well. A horizontal line, this is where you have a residual of 0. So if I see a residuals plot on my calculator that looks something like this, that tells me that a regression line is not appropriate for the original scatter plot because there's a pattern in the data that is not being explained by a line. Okay? It takes on a quadratic form. Probably, and this is a tool that we haven't looked at in this class, and we don't need to, it's not an AP standard, but probably there's a quadratic function that would better model, better pass through the data than a regression line would. Okay, so you're looking for patterns. Patterns are bad for a regression line if you're talking about a residuals plot. If, on the other hand, you've got a residuals plot that looks something like this, lots of bouncing around above that E equals 0 line, then that tells you that, yeah, some of the data falls above the line, some of the data falls below the line. okay? And there's no general trend there. A regression line is probably appropriate. You'll still look at R squared, but the residuals plot would be okay here for using regression line to go through your scatter plot. Okay, I know this is coming at you fast. Last slide that we'll talk about here real quick. We'll talk about high leverage and high influence points. I'm going to draw two scatter plots. Let's say X and Y are here and here. My first data set is something like that. My second data set is something like that, okay? So for the first data set, we have an outlier that I'm circling in blue, okay? It's what's called high leverage because it is far from the center of X and the center of Y, meaning that it has a lot of influence upon the correlation coefficient, okay? The correlation coefficient really listens to this guy because it's got a huge z-score for X, it's got a huge z-score for Y, all right? Now, it is not, however, not high influence. Why? Because if you took that data point out, you would still have a regression line that took on basically the same shape, regardless of whether or not that point is present, okay? On the second hand, you've got another outlier over here. This is a high leverage point, again, because it is far from the center of X, it's far from the center of Y, so the regression line, or not the regression line, the correlation coefficient really listens to the influence of this point, which is negative here, okay? Now this is high influence. High influence. Why? Because with that point present, the regression line is going to do something kind of like this. It still goes through the center of your data, but it tilts downwards because this outlier right here has a negative influence. Now, with that point removed from the data set, with that outlier gone, you have a regression line that looks more like that. So you see a big difference not only in terms of your y-intercept, before and after, but the slope changes dramatically too with that point present or removed.